is if you just Google Wanonta, they have some great simulations to play with, and it helps just make it, you know, more visual. So this, for instance, is a good one for solubility, to see that AB, A2B, AB2, and how the solubility constant, or solubility product constant, both is the same thing, how it varies according to the size of it. So if I, for instance, choose, let me just clear it, if I choose silver bromide, now what sort of salt is that? An AB, an A2B, or an AB2? An AB, right. And it's got quite a small constant of to the minus 13. So if I react it, so I'm putting solid in, then I will get, as you saw over there, initially I had, I'm pointing with my finger and you obviously can't see it, sorry. Initially I had no silver and no bromide ions, and with time, some of it, a very, very tiny amount dissolved. Remember, that's 10 to the minus 6, so it's not a very strong concentration at all, but a very small amount dissolved, and you can get equal amounts of silver to bromine, and that's why that line looks purple, because it's a red superimposed on blue. If I do calcium carbonate, which is also an AB salt, but it's a bigger constant, if I react that, can you see I have a greater concentration? So it's a graph of how much has dissolved. So when I added my solid calcium carbonate, then what is the concentration? So in the beginning I had nothing, but slowly with time more and more dissolved until it reached equilibrium. So it's just a visual to sort of see, you know, the more will dissolve, this greater, the bigger the constant. So the 3 to the minus 13 didn't go anywhere near as high, or 10 to the minus 6. If I go to that one, oh, sorry, you've got to go 10 to the minus 4 over there, so that's not as clear. But let me try a PbCl2, and if I react that, can you immediately see you've got double the amount of chloride? So when you're substituting into the expression, it's just a visual aid to help you remember you've got twice the amount. So it's you know, it's so you can go through all that. Another one is okay, no, that's pH. We're doing the common ion today. So this is another one you can do. So remember, last week we looked at, will a solid precipitate if I mix two solutions? Okay, so this is where you calculated the IP. Now they've got Q for quotient. It's the same thing. So it just depends. I mean, when I was at uni, I learned it as Q, but in New Zealand, I've seen they use it as IP. It's the same thing. It's simply the solubility product expression, but not at equilibrium. So you calculate it and see how it relates to the equilibrium solubility product, to see, will something dissolve more, will it precipitate, or what's going to happen. So you can just play around and go, if I increase my amount of lead ions and just increase some of my chloride ions, what happens to my IP? And you can see I'm substituting into that solubility product expression. Yep, so the solubility product constant is actually Ks. Okay, Ksp is the same as Ks. So that constant is fixed at a particular temperature, but we calculate it by using the ratio of the products raised to their stoichiometric power. So PCl2 forms one lead ion and 2 chloride ions. So chloride is raised to the power of 2. So if we substitute these values into the KSP, then we can see, I'll answer your question just now, April, we can see, is this bigger or smaller than the KS value? So if I have those concentrations, I get to that, it's smaller. So will I get a precipitate or not? I won't get a precipitate. Good. Okay. If I increase my concentration, say I had much more chloride, okay, say a little bit more of this. I'm just trying to make it go bigger. Can you see now it's bigger? And so I will get a precipitate now. So you can play around with the different ones because they've all got different solubility products. So going back to your question, April, but then this is not a constant. The solubility product is a constant. It's just a constant to a particular temperature. So if you don't change the temperature, you only change the pressure or the concentration or whatever, that constant is constant. IP is that same expression, but it's not at equilibrium. So the only difference between these two, the KS and the IP, or the Q is the same as IP, the only difference is that this one is not at equilibrium, and this one up here is at equilibrium. So what's going to happen is if I mix these two solutions of iron and hydroxide together, then initially I won't get a precipitate because I've just mixed them, but then with time the ions will collide with the hydroxides and I'll start getting a precipitate as there's more and more collisions until it reaches equilibrium conditions, and that's when the Q, so for every collision that happens, this is the concentrations are going to decrease here, because you can see if the ions are going to be iron ions are colliding with hydroxide ions precipitating, you can see these are going to decrease until this value reaches that value, and then it has reached equilibrium conditions. So as I mix them, this value is going to keep on changing as it precipitates out. So what we're just doing here is working out at the instant of mixing, will I get a precipitate or not? If it's bigger, I will get a precipitate. If it's smaller, I won't. Does that make sense? So we're just sort of using this as a measure to see if we're going to be getting a precipitate. And as the precipitate forms and it reaches equilibrium, then this Q value will be changing and eventually land up the same as the KS value. Okay, so this doesn't change. This one does as it reaches equilibrium. Why would you? So yeah, that's why we don't call it. We don't really call this a constant. We call it the quotient for Q, or we can call it. I'm so used to saying IP, something product. I've written it in your books. You may know. I've gone blank. Ionic product. Thank you, Caleb. So that's not a constant. So thank you, April, for pointing that out. It's just an ionic product. Where we multiply the ions. Ionic product means multiply ions. Okay, but that is the constant, so it gets given a K. So you'll come across Ka, Kb, Ks, those are constants for a particular temperature. Okay. Right, so you can play around and, see, will something dissolve or won't it? Okay. And so does it mean how many ions are in versus the number of salt? Sorry, Joe, I'm not quite sure what you mean there. We don't include the solid. Yep. So it looks at how the ions in solution, because we taking the solid and dissolving it, and when it's saturated, then this is in equilibrium. So in other words, as many lead chloride dissolves as lead and chloride collides and forms a solid again. So in other words, the forward reaction rate is equal to the back reaction rate. I don't know if I've answered your question there. You don't need to separate the ions in terms of individual products. Well, for the, these ions are separated in solution. So you're going to have, a lead ion and a lead ion and a lead ion and a chloride ion, all separated out. Yep. And then you've got still your undissolved solid. That's sitting there. Okay. You don't need to know the quantity. So you mean the concentration of the ions. They will be given. So for an IP type question, they will give you the concentrations of two solutions. So they'll say, if I mix what's this one? A calcium chloride solution, which has a concentration of 1 times 10 to the minus 4 moles per liter, okay, with a sodium carbonate solution, which has a concentration of 1 times 10 to the minus 2 moles per liter, will I get a precipitate when I mix these two solutions? So you know that the carbonate comes from the sodium carbonate, okay, and there's 1 carbonate for every 1 sodium carbonate, so it's the same concentration. Okay, so that's what you substitute in there. And if this was a calcium chloride, then 1 calcium chloride gives 1 calcium ion, so that's, you substitute into there. Okay, the spectator ions, the sodium and the chloride, remember, although we talk about sodium chloride, it actually doesn't exist, because you've got the sodium ions and the chloride ions just happily in solution, as happy as Larry, and they don't combine ever. They'll collide instantly, but then they'll dissolve again because they are soluble. So I know, we teach that if we mix these two solutions, they swap partners, but actually that's not true. If you've got soluble ions, they are separated before you mix them, and when you mix them, if they're still soluble, they will stay in solution. So in my beaker here, I'm going to have sodium ions and chloride ions all happily wandering around, and they don't affect this equilibrium at all, because you can see it, it's not in here. They're not a common ion or anything. So we don't have sodium there or chloride in there. Okay, so what I wanted to show then, the common ion effect, is what happens. Now here they've got this ice that we looked at, and I'm going to just pull this down a bit. Okay, so your change, so while it's happening and reaching equilibrium, okay, and then your final equilibrium concentration. So you can choose any of these. So here they've taken lead chromate, okay, and I dissolve that amount into a solution also containing lead. So I'm dissolving it in a 0.01 moles per liter solution of lead nitrate. So the lead is in solution, the nitrate's in solution, but now I'm adding some solid lead chromate. How much of the lead chromate is going to dissolve? So if we were trying to dissolve it in pure water, then it's just dead easy. We just say Ks is equal to S squared and solve for S. But because this is not pure water, it's a solution of lead nitrate, and we have a common ion of lead, okay? So it tells you the common ion. So we have to work it out and do our assumptions. So remember, always list what you've got. Always remember the EQ method, the equation. That always comes first. And then, okay, the expression I would have put next so you know what to multiply. Now, in the beginning, okay, they're first doing, oh, okay, sorry, the lead nitrate, they've made pure water. So what they're doing here, sorry, this isn't pure water, because can you see there's no lead nitrate here whatsoever? Okay, so in pure water, this is the solubility. So they're just solving, you know, Ks is equal to S squared. If I increase this, so now I've added a common ion. So now, instead of being 0, as I had before, I now have it as 0.3. So can you see the 0.3 there? But I've got no chromate in the beginning because I haven't added my lead chromate yet. Now I add my lead chromate. My lead chromate is going to start dissolving. So if X amount dissolves, I'm going to get X amount of lead and X amount of chromate. So at equilibrium, it'll be 0.3 plus X, and the chromate will be X. Now, can I assume that X is tiny compared to 0.3, so I can ignore it? Yes. So when I substitute, and I must say this animation or simulation isn't really good because it doesn't show you the expression and then the substitution, it just gives you the answer. But you would substitute the 0.3 in for the lead and X for the chromate. There's your solubility they haven't given you the solubility product either, but yeah, okay, but then they give it to you like that. So it's just to give you an idea of how these, you know, how the solubility changes as we add more lead. Okay, so as we add more lead, do you notice the solubility decreases? So Joe, if it's that's a good one. So if we take let's say AgCl, no, that's a 1 calcium. I'm trying to, these, okay, there's one with the chloride. Okay, so let's do it with chloride. So initially it's pure water. We don't have any calcium and chloride in there. Okay, so our lead chloride dissolves to form lead ions and chloride ions. So that is my solubility. So lead chloride is starting to get actually quite soluble because it's 0.0016. Sorry, 0.016. So it's, the assumptions are going to start being a bit tricky now. But as I say, the ones we give you are pretty good. But as I add this, okay, then I've got now more and more chloride to start off with. And so I've got the 0.3 plus the 2x. But again, so you said, do we use the powers? I can ignore the 2x for chloride because it's tiny, you know, it's tiny enough with the point compared to the 0.3. but I still have to square the 0.3. So in that respect, yes, I do need to square it, because my Ks is equal to Pb concentration times chloride concentration squared. Okay, and as you notice, as I increase the amount of chloride, it becomes less and less and less soluble. So I've got more, fewer and fewer dissolving. Okay, so that's the common ion. What I want to do now is go to my PowerPoint. Joe, no, it won't be 2x squared. That's actually a good question, because a lot of students get confused about, it's 2Cl, so I've got to double it and then square it. That only works when you are dissolving in pure water. Because I'm saying, right, I've got lead chloride, and if I put it into pure water, say I had 0.1 mole per liter solution, I'm going to have 0.1 mole per liter solution of lead ions, and I'm going to have 0.2 moles per liter of chloride ions. I've doubled it. Then I take those values, those concentrations, and I substitute it into the expression. So I say 0.1 times 0.2 squared. So that's what you're thinking of. When I have a common ion, the concentrations are over here. Okay? I don't have to double it, because that 2x is already the doubling part, and I've ignored it because I've said it's tiny in comparison to 1. So I just have to say the solubility product is equal to x times 1 squared. Does that make sense? So when you're doing the common ion, you don't double, you won't be doubling the KCl, because that's where the chloride's coming from. So where you've already got the concentrations, you don't double. You only double. The best way, Joe, is to go through problems and then see that. Yep. So Johnny, if it's unfortunate they've got no example here of the salts where it's 2 Pb plus, say, 4O or something like that. If it's a so there, yes, this would become x squared and whatever, but and it would be twice. So that if this was 2, then this would be 2x, and then you'd square it. So yes, in that respect. I'm just wondering actually if I've got no, I don't think there's an example like that where I could do that. The common ion, there's F, so that's still squared. The common ion, there's chloride. Yep, sorry, because there's no like Pb2 something or the other. So yep, but if it was, then you would still do that. So in other words, a 2x squared, because you can't then ignore the I can't say that that's tiny in comparison, so I can ignore it. Okay, so yeah, Joe, I suggest, have you worked through the booklet yet? Because as you work through it, then do the problems, and you're getting there, okay? Because we can always put more problems together, practice problems. It's just, as I say, it's identifying whether it comes from a single source, and then you do the double square, you do the straightforward S squared. When it's when it's separate sources. So it could be what we showed here when we were looking at the IP. Those are different sources, so we don't double and square automatically over here. Okay, we just simply use the concentrations that are given. Common ion is the same thing, 2 separate sources, so we don't necessarily double and square. Okay, depends on the exact problem, but it's not an automatic thing. When do we? It would be in the cases like what John Lee said, if it was, say, this X that we didn't have anything to compare with, so we couldn't ignore it, and if that was a 2cl, and as I say, we don't have a problem with that. Yep. So the best is actually sort of to work through it, and then you'll see it. I don't think I've convinced you in any way, but as you work through problems, it'll start becoming clearer. Okay, so let's go through this PowerPoint, and then I want to just show. Okay, this was the Le Chatelier's principle again. It's just to show you, of course, my Ks value stays constant. These concentrations can change, but the value stays constant for a particular temperature. So if we add, remember I added more, then I'm going to get a backward reaction, and some of it has got to precipitate. And of course, for every silver that goes backwards, I've got to have a chloride that goes backward to form the silver chloride. And so when it reaches equilibrium, then my Ks is still 4, but you can see my concentrations have changed. Okay, so I had initially added more silver, but some of it has gone back. So that is at Le Chatelier's principle. The stress was, or the change was adding more chloride, so the reaction is going to work in such a way as to remove that stress or to remove that change. So if we're adding silver, it's going to try and remove silver. Or if we remove silver, it'll try and add silver. Okay, right. And so those are just the two things that if you change the one, the other one will also change. Because if this reaction goes backwards, I'm decreasing the silver ions as well as the chloride ions. Okay, so that is at Le Chatelier, and it's, you need to know that for the next bit. This is the common ion, as I was talking about. Complex ions, you definitely need complex ions if you want excellence, because there's definitely going to be a question on complex ions, because that's what they use for the excellence thing. And then pH. Now we're going to learn more about pH in the 306.2, but any insoluble salt that has an acidic or basic ion in it can be affected by pH. So this could be hydroxide, carbonate, because it's a conjugate base of carbonic acid, phosphate, it's a conjugate base of phosphoric acid. Nitrate does not, because although it's a conjugate base, it's a conjugate base of nitric acid, which is a strong acid. Now, if I talk about strong acids and weak acids, does that sound familiar? Yep. Okay. So we'll, 306.2 deals with it all over again anyway, and we'll be doing that. So if you've got anything that's the conjugate acid or base of a weak acid or base, it's going to be affected by pH. So you usually don't have to do calculations, but you have to do explanations for this sort of thing. So let's have a look. I'll always call them. Okay, do we need to learn these conjugate acid base things in 306.1? No, I deal with it in 306.2, but then I do refer to a few things as you go through it, and in the final teacher marked assignment for 306.3, you'll probably get a question like that. There may be actually, I think in the 306.1a, something on phosphoric acid with a phosphate. What would happen to a particular thing? I think it's a phosphate salt, because that's, so it may come in there, but don't worry, you will learn all about it as you go. Now anyway, these, okay, that's fine, you 306.2, you'll come across them. Zac and Zelp. I must admit, I do know a few Zacs. I don't know any Zelps, but So you can, if you ever have a child, you can call it ZELP if you like. Okay. ZAC and ZELP are your memory aids for for complex ions. So I've sort of made ZAC a little bit lighter in color because he relates to ammonia. Okay, so any complex ions formed with ammonia, ZAC is your memory aid. Any complex ion formed with hydroxide, ZELP is your memory aid. So what does ZAC stand for? It's zinc, silver, and copper. All these three ions, when you add ammonia to it, no, bleach is actually not ammonia. In fact, never, ever, ever mix ammonia and bleach together. You'll kill yourself. Okay, it gives off amine type compounds, chloroamines, which are very poisonous. Okay, so if you ever do that, do it in a very, very well ventilated space. There have been deaths actually where cleaners have used ammonia and bleach in a toilet, and the fumes killed them. Okay, so last lesson. Okay, so never bleach and an ammonia compound, because as I said, the chloroamines are very poisonous. Okay, yep, so this is ammonia. You can buy it in the supermarket as Scrubs ammonia. Some window cleaners have ammonia in it. Okay, what happens is when you add ammonia to a solution of zinc, whatever, then the zinc will first precipitate. And the reason why it precipitates is ammonia is basic. So if I add ammonia to water, because remember, if I'm adding it to solution of zinc, there's water present. So what will the ammonia do to water? What ion is going to form? Hydroxide. Correct. Okay, the ammonia reacts with water from the hydroxide. So Joe, if you're not sure about that, I promise you it is dealt with in 306.2. So you'll get there. So when you add the ammonia, you get the hydroxide, so the zinc precipitates out as zinc hydroxide. But then if you keep on adding ammonia, you'll find that that white solid of zinc hydroxide starts dissolving again. And then it's totally gone. Okay, it's all in solution. And that's because it forms a complex. Zinc, an aqueous zinc ion has got zinc surrounded by normally 6, sometimes it's 4, but I think for zinc it's 6 water molecules. And those can be replaced by other, what we call ligands. So water, the oxygen has got a lone pair, and it uses that to sort of bond onto the zinc, to attach itself onto the zinc, you know, because it's more negative, and zinc is a positive cation, so there's that attraction. So chlorides can do that, ammonia can do that. So you can get all these different ligands that can actually complex onto the ion. So it can do it for zinc, silver does that, and copper does that. And copper is actually a beautiful royal blue when it does that. ZELP, on the other hand, is for hydroxide, and this forms a complex again zinc. Okay, so if I kept on adding hydroxide, if I first add hydroxide to a zinc solution, I'll get my zinc hydroxide precipitate. And as I keep on adding, I'm going to get more precipitate. But as I keep on adding, that precipitate is going to start dissolving, because my zinc hydroxide, or any zinc formed, is going to form the complex. And then I'll be using my equilibrium, it'll go the reverse reaction, so that more and more will dissolve. And I've called it, as I say, ZELP. The L is to remember that this is aluminium and not silver, or P for plumbium, you know, lead. That's why I put that L in. Now, another tip to help you remember the complex ions, because you have to actually give the formula for it, is all the complexes for Zach and Zelp, apart from this silver one with ammonia, forms 4 ligands around it. So 4 ammonia molecules or 4 hydroxide molecules. The exception is with silver, it only has 2. Okay, and the charge is very easy to work out, because if I have zinc with 4 ammonias around it, what is the charge on the zinc ion? +2. If I'm adding 4 neutral NH3 molecules, is my charge going to change? No. So the charge on the complex ion of zinc with ammonia is +2. However, if I take zinc and I make a complex ion with hydroxide, the charge on the zinc ion is +2. But if I add 4 hydroxides, so 4 negative charges, great Johnny, my complex ion charge over here will now be -2. Okay, and of course the silver one is, because the charge on silver is +1, so the complex ion is +1. Okay, so what I've got here is, just so that you see, they're pretty colors. So there's your copper, and as I'm adding the ammonia, can you see I'm first getting that bluey precipitate? That was the copper hydroxide, and now can you see this beautiful, oh, there we go, back a bit. Can you see that beautiful solution? So that is your copper, that is your copper complex, okay? This bluey thing. So initially that blue precipitate was copper hydroxide. Okay, bye April. And this is now your complex ion. So here, down here they have again your copper, and they're adding hydroxide. So that was adding ammonia. So here, notice, remember our Zach and Zelp. We don't actually have the copper in our Zelp with hydroxide. So did you see that this has not dissolved? So I've added hydroxide, I keep on adding hydroxide, and I don't get anything dissolving because there's no complex ion formed. Here, if I add ammonia, because to this one they're adding ammonia, okay, sorry, they're waving around in the wrong place. But anyway, you can see that sort of precipitate of the copper hydroxide coming out, and as they add more, we're going to see that lovely blue color that we saw up there. Okay, so frankly chemistry, and this one is Farnborough, if you want to have a look. Okay, right, this is now, oh, he does all of them. You don't, he's got one mistake, I think, in one of these. You only have to know the zinc, aluminium, copper. You don't need to need the iron. Sorry, I'm just going to turn this volume down because I can hear it even if you can't. So have a look at that. But as I say, you don't need the Fe2 plus or Fe3 plus. It's not in the standard. But I mean, if you want to know what happens, you're welcome. Okay, so you'll see there the zinc, it's a white precipitate, and as you add more hydroxide, it will dissolve. Okay, and here is zinc with the ammonia. So it's the same sort of thing as what we saw before. So there's first the zinc hydroxide precipitate, and as he adds more, it starts dissolving. Oh, hang on, he actually said zinc, and it actually first is magnesium, and magnesium doesn't dissolve. So let's get zinc. Zinc is at 4 minutes and 5 seconds. Okay, so there's the zinc. You can see the zinc hydroxide precipitate as you add ammonia, and as they add more, then can you see it's dissolved? Okay, so you do need to explain the complex ions. So there are the complex ions you have to learn. Okay. And the way you explain this is in terms of equilibria. And I will have some exercises in the next slide. I've just mentioned here as well the pH. These can also be affected when you change pH. Hydroxides again, you know, we had hydroxides here because of complex ions. Here it's hydroxide with pH. So sometimes they might give you something and they're looking at, if you remember that it's both complex ion and pH that's coming into it. So, you know, it depends on the question. So anything which is a conjugate base of a weak acid. So carbonate, hydrogen carbonate, hydrogen phosphate, dihydrogen phosphate, and phosphate. That's an acid. It can't be a conjugate base, so okay. Right. So this is a from the 2013 exam, and notice they say no calculations are necessary. So what they want here is I'm adding a chromate, silver chromate, okay, and then here I'm having silver chromate in an ammonia solution. So that one's pure water, that one's ammonia. So there's no common ion, but I've got something that can complex. So silver ions, here is a straightforward equilibrium between the silver chromate and the, you know, and its ions. Here, what will happen is that the silver ions can form the complex. So write your equations, and then you can say in this equation the equilibrium position shifts to the left or right, you know, from the Chateliers, and state which way the position shifts. I know some examiners get quite fussy. You can't just say the equilibrium shifts from left to right. They say no, it's the position of the equilibrium that shifts from left to right. So as an example, in beaker 1, all I've got is my pure solid and my ions. So when that reaches equilibrium, I'm going to have X amount dissolved. With this one, not only will my silver chromate dissolve in the same way for beaker B, so this equation also applies, but then I'm going to have a further reaction where my silver ions will react with the ammonia present to form the silver ammonium complex. So what do you think will happen? Will more dissolve in beaker B or less dissolve in beaker B? More, correct. Because what you're going to say, you know, you're going to form this equilibrium, but then the silver ions is going to react with the ammonia. So the stress is removing the silver ions, because we're removing it to form the complex. So if I'm removing this, the equilibrium position of this equation is going to shift to the right to try and replace the silver that I'm removing. So write your equations down, call them equation 1 and equation 2, if you find that easier to refer to, and then say, you know, equation 1 happens in both of them, but in both beakers, but in beaker B, the silver ions react further, as shown in equation 2, and so the equilibrium position of equation 1 will be shifting to the right to try and replace those silver ions that are complexing with the ammonia. Can you see, you know, the explanation? So equations are really important. Write your equations down and then explain it. Okay. And then, as I say, sometimes these sort of explanation type questions can have a little things in there, you know, so just make sure you've read it and you've answered all the bits to it, because you've got to think about pH at times. I mean, you could actually talk about a silver hydroxide precipitate here as well if you really wanted to, but I think they weren't looking for that in this one. Okay, so here's one where we're looking at the pH of iron hydroxide. So write the first equation, you know, the standard solubility equation, and then you can refer to that. Think of anything else that could relate. So if I decrease the pH, then I'm increasing the amount of hydronium ion. So I've written an equation here to show the equilibrium between water and its ions. So if I'm decreasing the pH, I'm increasing this. So if my stress is adding this, which way is this equilibrium position going to shift? Towards the left to make some more hydronium, or towards the right? Towards the right. And if it goes towards the right to form water, to form more H2O, what's going to happen to my amount of, or my concentration of OH minus? It's going to be less. And so if this is less, then I've added a stress to this system. So if this decreases, which way is this equilibrium position going to shift to try and relieve that stress? It's going to go to the right, and so it's going to dissolve more. Okay, so you would have to discuss those things. Now, Joe, you've said you've never seen this H3O plus ion before. That's the hydronium ion. At level 2 and at level 1, we talk about the hydrogen ion. But the hydrogen ion is actually a proton, because hydrogen is an electron and a proton. So if I strip the electron off, I've just got a proton. Now, a proton will not exist by itself. It is just way too reactive. So the way chemists use it, they attach it. So if it's in water, they attach it to a water molecule. In reality, it's actually got quite a few water molecules around it. So you should, strictly speaking, have a brackets around, attach that to another water molecule and another water molecule, because a proton is just so, I mean, it's tiny and it's a whole positive charge on it, so it's just going to attract all the water around it. Okay, but we just represent it by an H3O plus. Okay, there shouldn't have been that space there by the plus. Okay, so basically you talk about impure water, what's going to happen, and then if, can you see I'm spelling it out? If I decrease the pH, I'm adding hydronium ions. So you could not have equal amounts of H plus and H2O. Well, I mean, if you made, actually, I doubt it, because you would have to have something incredibly acidic to have that many H plus ions, actually, because water is round about 55 moles per litre. In other words, you've got 55 moles of water molecules in 1 litre of water. And I've never ever seen a solution, an acidic solution with 55 moles per litre of acid. So yeah, I think in practice you could never have equal amounts of H plus and H2O particles. I don't know if I've responded to your question, Caleb, or if you were talking about the proton surrounding itself by water. Because I actually think you couldn't dissolve that much acid. Yes, yeah, yeah. I think you could never get something that acidic. So to answer your question, no, I don't think you could ever get equal concentrations of water molecules to hydronium ion molecules. Okay, and then can you see I've labeled them equation 1, just to make it easier to explain, And so I've said more dissolves, and can you see I've answered the question as well? So if I lower my pH, I'm going to get more dissolving, because they're saying effect of decreasing on solubility. So you make sure you've got that statement somewhere. Okay. So here's another one from the 2011 exam. Okay, zinc hydroxide, and I've only got a small amount of solid zinc hydroxide at the bottom of the container. I change the pH. Thus discuss the effect of increasing the pH. Now, whenever you get these sort of problems, think of Zach and Zelp, because they're clues. Will a complex ion also figure in the discussion? Okay, because here we're talking about pH, so we've got to discuss the effect of pH, but we've also got the complex ion. Okay, and remember, Zach and Zelp are both with Z, they're both zinc. So you first give your basic solubility equation. Okay, then we're increasing the pH. So we're adding OH minus. Actually, I should have given the water one first, but I've immediately thought of complex ion. Okay, and I should have actually also included that water equation, because as I'm increasing my pH, I'm adding OH minus. So initially, if I'm adding OH minus, which way is this equilibrium position going to move? To the left or to the right? To the left. So as I increase my pH, I'm going to get more precipitate. Okay? It'll become less soluble. I will get more solid being formed at the bottom of the beaker container. But as I keep on adding my OH minus, okay, I keep on adding, I'm increasing this. So if I'm increasing my OH, and I've got now more and more and more OH minus present, I'm now going to have enough OH minus to start surrounding my zinc ions. And so this is going to shift to the right. If this shifts to the right to form the complex ion, I'm decreasing this, because if it shifts to the right, I'm decreasing that, which means I'm decreasing that. If I'm decreasing that, which way is this equilibrium going to shift? To the left or the right? To the right. So what's going to happen is I add my hydroxide, I'm first going to get more and more solid being formed, and as I keep on adding, I've eventually got enough OH minus there to complex, and it'll start dissolving the zinc hydroxide, because it's going to start shifting to this equilibrium position will start shifting to the right to try and increase the amount of zinc that's disappearing into this complex. Okay, and this sort of complex ion actually happens in your body. Do you know of anybody with kidney stones or anything like that? Have you? Okay, they're often given a citrate. You know, first stoppers have these tablets. They citrate tablets, because calcium, most kidney stones, I mean, if kidney stones vary, but are like calcium oxalate or something, and the calcium forms a complex ion with citrate, and so they hope by, if you're having enough citrate in your body, you will dissolve the calcium out of the kidney stone, so it then dissolves. Yes, they hope. Because of course you don't want too much citrate. I mean, citric acid is great for you and so on, but you don't want too much, because of course you've got calcium in your bones too, and you don't want all the calcium in your bones dissolving. So you know what they say about medicine, it's all in the dose, whether it's going to kill you or fix you. Okay, yes, so so urine infections is something a bit different. Okay, that's bacteria and so on. I'm talking about the kidney stone. So anyway, so that's where complex ions come in quite a bit. Okay, so, you know, explain, when you read over your statement, then your explanation, look at it from the point of view, like, is my teacher's really dumb? I need to explain every little point. Is it clear what equation I'm referring to? Is it clear what ion I'm referring to? Is it clear, what is happening? Okay. Right, so these are urine infection changes the pH of your. It could be, so I don't know. I know your pee also depends on what you eat. So normally it's round about pH of 6, but you can have very alkaline pee and you can have quite acidic pee. So, okay, Johnny, you would know more. I only know a little bit. But yes, it's but yeah, I suppose if the pH of your pee is very different, very acidic or very basic, then it's obviously a pointer that not everything's right, or your diet is really wrong. Okay, and there was that final step, okay, about the complex ion. Right, so common ion problem, very quickly. Actually, no, we've done this one. This actually is an extra one, I think. Yep. So we don't do that. So if I go back to, it is now more or less 4 o'clock. Yep, so this was the solubility in pH. Remember we're talking about the pH. Here are all the different hydroxides, and as you change the pH, notice what's happening to how much will dissolve. So, okay, here I'm just increasing my pH. Okay, now it's starting to dissolve. So I had to increase it by quite a bit before there was an effect. Okay. So less and less and less dissolves. Can you see it's getting smaller? So as my pH is getting higher, I'm having less dissolving. Let's take, they haven't got really complex ions here, but I mean it's just to play around. So here if I've got a low pH, then quite a bit has dissolved, but as I increase it, hopefully I'll get to the point where, okay, then I'll have got some of the ions. But it's just to play around with if you want to play on that. It does give you a description of what to do. So it says the solubility equilibria containing hydroxide ions are influenced by pH, okay, and so on. I think we'll stop there because we've now finished 3061 and I don't want to go on to 3062 because that's now on acids and bases. So we'll do weak acids, weak bases and all that stuff next week. Okay, great. I'm glad it's not so complex. Okay, and Joe, as I say, if you get stuck with something, work through more problems. If you need help with more problems, email me and so on, so we can just work through the problems. No brain too small, by the way, is a great, sorry, two should be TOO, is a great site to use. So they've got lots of extra problems and questions there. In fact, let's go there now, very quickly. I know Johnny has been here because I told her last year about it. So no brain too small, there's quite a few, let me just make it bigger. So there's level 2, level 3 chemistry here as well. So Joe, if you wanted, and so if you were looking at this, then you know, they've got flashcards, help sheets, essential questions, and so on, collated questions if you wanted to work through. Okay, lots of things like that. Another good site to use is Science Scribe. So particularly for this one is he's level 3. He also does level 1, level 2, level 3. But what's good about this one is he's got YouTube clips. These really apply more to the 3062 and 3063. Yes, that's correct. She's actually at a different school now. So that's a useful source. And then, of course, don't forget best choice. So those are all, if you're trying to look for things to help you before the mock exams, which are coming up quite soon, then those are 3 good sites to go to. So No Brain Too Small, this one, Science Scribe, that one, and as I say, both of them have level 1, level 2, and level 3. So if you're wanting to back up some things, and then Best Choice is the other one. So if I just do Best Choice, I've already signed in. If you haven't signed in, you need to hang on. So you'll see there's year 13, you would be logging in and so on, and there is here, for instance, the equilibrium, acids and bases, there's solubility, equilibrium, and precipitation. So they have lots of, this is just the overall thing, but you can work through it. Oh, I clicked on redox. Oh, there's KS. So KS, solubility, equilibria. So you click on there, and there's a whole lot of problems you can work through and explanations. Okay, so those are 3 good sites for revision.